Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN, sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good afternoon, everyone, and welcome. In recent years, AI breakthroughs have largely focused on text and images powered by massive natural models. But in most organized organizations, the dominant data format remains the spreadsheets, relational database, and data warehouse, so tabular data. Despite its importance, tabular data has historically received less attention from the deep learning community, from the researchers community, and this is now changing with the rise of tabular AI. Today's session explores how neural models can understand tabular data, how table semantics can enable safer and more powerful data use, and how AI is transforming table retrieval, creating an end-to-end analytical pipelines. We will also reflect on what the future of tabular data science looks like and the skills it would require. It is now my pleasure to introduce our speaker, Madelon Ulsebos. She is a leading researcher at Centered Wiskunde in Informatics, CWA, where she leads the Table Representation Learning Lab. Her work on tabular AI sits at the intersection of machine learning and data management. Today, she will guide us through neural approaches to tabular data, AI-powered table retrieval and reasoning, and forward-looking perspective on the future of data science systems. So please, join me in welcoming Dr. Madelon Ulsebos.
Thank you very much, Cecilia. Thank you very much. Thanks for the invitation. It's really a pleasure to be on this series. Actually, I really look forward to also the discussions in the end. But before, let me share the screen with you for the slides. But before we get to the end and the discussion part, of course, I'll go into the direction of, or I'll address the work that we've been doing on tabular AI. And before doing so, I'd like to really motivate why this is such an important topic towards the democratization of insights from tabular data. But of course, before we get started, I'm happy to introduce myself a little bit and where I'm coming from. So my name is Madelon. I am Dutch, and I've been educated a lot in the Netherlands. So I started at TU Delft, did my PhD at the University of Amsterdam, and now I'm at CWI, which is in Amsterdam, where I'm also affiliated with the Alice unit there, which is a very large and exciting unit to be connected to. Throughout my academic adventures, I've been doing research with MIT. I've been also doing a postdoc at Berkeley. And in the meantime, I've been also in industry, where I started off as a data scientist and later on did research work in industry. Now I'm at CWI leading this TRL lab, which stands for Table Representation Learning. You can check out my personal website or the lab page that we have here on this slide. And what we're working on and towards is this vision of democratizing insights from tabular data. And why I think this is so important and valuable to work on is because tabular data is really prevailing, actionable, and very critical to so many tasks that we're actually working on and seeing in organizations. And the sub-goals of that vision starts with bringing data scientists and data analysts from 1 to 10, so they can really focus on things that actually really matter, and everyone else from 0 to 1. So really democratizing these insights to people that might not have coding skills or, data analysis skills, etc. And this involves, as you will see also during this presentation, this involves tabular retrieval, querying, table semantics, now also end-to-end data science pipelines, predictive machine learning, and more. So what brought me to this space is actually this moment where I was a data scientist in industry, and I made three key observations. The first being that tables really prevail in the organizational data landscape. So whatever task I was working on, I noticed that across different companies, most people are really working with relational and otherwise tabular data from CSV files, for example, or relational databases. So if you consider, for example, the popularity of database systems, you really see that the relational database systems in industry are by far most used. But also if you consider the datasets in the wild, so for example, through Google Dataset Search, which indexes all the datasets on the web, you also see that tabular data is really the dominant form. And of course, that is for a reason, because these tables really serve high value decisions. So that was one. As a data scientist, I made another observation, and that is that everyone was basically doing the same. So here you see a few Kaggle notebooks, and this is of course on Kaggle, but I realized that we were like repeating the same kind of data science pipelines over and over again for different tasks, but also for similar tasks across different companies. And doing this over and over again, you start to realize like, oh, maybe there are patterns that we can actually learn from tables and code, right? So that was another indicator that there is a lot of value in machine learning for tabular data. Now, why I think AI can actually help a lot and where mostly is if you consider the whole end-to-end nature of data science pipelines. Because what I also noticed that although I was a data scientist where I thought I would focus on like building machine learning models, that was only like, as they say, 20% of the work. 80% of the work was actually, as they say, data work. So I was doing a lot of data collection, retrieval, data search, data integration, data cleaning, feature engineering, etc. And that really constitutes 80%. And that 80% is super, super time consuming. So that's why I think that AI really like enables us or would enable us to do this more efficiently. And it's actually a useful tool, let's say, to democratize insights to tabular data. But, and this was back in 2019-ish, 2020. You would think, oh, we have AI now, and I think we started seeing all these fancy deep learning models, and it was fascinating, but they were mainly built for text data, for images, and nowadays we see a lot of like code generation, but all these tables, they were just largely ignored as if people just, I don't know, or they could not access data because tabular data is, of course, very privacy sensitive often. So there was just not enough data, perhaps, to train large-scale models. But if we would have such corpus, we could actually try to train models that are able to work with all this tabular data. And that way we can actually democratize the insights that are stored inside of them. And I think the deep learning revolution has really started off like a couple of years ago now for tabular data as well. So that is really great to see. So that concludes the kind of motivational side of why I'm working on tabular AI. And now I'll briefly introduce the kind of key components of this seminar. So in the first part, I'll briefly elaborate on table representation learning, what it is, what are the key challenges, and also the key techniques. Then I'll move towards insight extraction, so more application focused on table retrieval, semantics, and reasoning. And finally, I also want to, and I hope this can actually spark some interesting discussion, I will attend to the end-to-end perspective, which might be actually the future of data science, question mark. So let's get started on the first part. What is table representation learning? And I think that is best kind of started with addressing the challenges to understand why particular techniques are introduced. And the first challenge is that of data heterogeneity. So instead of text, for example, and text can of course also, or free-form text, let's say, can be quite heterogeneous as well as like documents, etc. But tables come with really mixed data types and fairly little context. And they come in all kind of shapes, semantics, and sizes. Shapes in the sense of you can have spreadsheets, right, with perhaps a few hierarchies or layers of dimensions. But you can also face like relational data, which is more perhaps a bit more structured and more organized in the 2D format. And then you can face like any kind of semantics of these tables. So how can we actually deal with all the variations that we see of tabular data? That's one particular challenge. The second challenge is that of particular properties that consider these relationships within the data. So you have, for example, a single table, but within those tables, you have relationships between rows potentially, or relationships between columns. But we should not forget that actually the order of these relationships are not like, these models should be order invariant. So for example, you might see a column in a certain place, but in another table, you might find it like very, in a very different place, but it doesn't really change the semantics of this data set. But besides the relationships between different columns and rows, for example, that might or might not be there, we should also take into account the relationships of tables with other tables. So particularly from a relational perspective, we see, or we need to take this into account, that certain tables are related and might actually need to be joined before you can execute certain operations. Another challenge of tabular data, I think, is that tasks over tabular data are very multifaceted. So if you consider a data analysis or data science pipeline, you're dealing with lots of different operations. So this goes from storage to retrieval to, you might need to process this data, cleaning, integration, etc., down towards the final analysis. And depending on the kind of insight need, that really determines what kind of steps you need to take here. But for many of these tasks, you need to have particular models. So you cannot just try to address everything with a single model, or at least in my view, that might not be the best idea. So the question then is like, which tasks involve general knowledge, for example, which could be solved perhaps or enriched with LLMs? Which ones need domain-specific insight, or which ones require analytical or causal reasoning? And these kind of questions determine what kind of model you would need for this, and what kind of architecture and representation of the data that is most suitable. And as I said, the question is, should one model do all of this? Can that even be done? And what are the limitations then? So yeah, I do think that the deep learning kind of revolution is very, very relevant also for tabular data, and that many of these challenges can actually be addressed by using machine learning, and particularly representation learning for tabular data. So what then is the gist of TRL? Is to map each table, or potentially multiple tables or potentially subsets or like subsets of data of a single table to some consistent input, and then learn representations on top of that that helps us detect patterns that are relevant then to different tasks. And of course, as I just said, given the really multifaceted nature of tabular data analysis, I think we should be really mindful of which tasks make sense to group in one model, let's say, and where to split these model capabilities. But that is the general idea. So how does that then work? I thought it would be good to give a brief overview of that, where I'll mainly focus on typical question answering tasks over tables. So you start off with a table. As input, you might have a question. You then provide that in this model. I'll get into the details in a bit later. And then as output, you might either have embeddings or a label, which then typically is a tuned model, for example, that predicts the right label for this question. So how do we go from that input into that model? So here you have this question and this table. What we typically do is we first serialize these questions or tables. So what we do is we of course need to flatten this table into a sequence. So we might just add like all columns and then all rows, or sorry, not columns, but like the headers, and then all the values of the rows. Or we might do it in a different way. So then we do like column-wise serialization, where we serialize data row by row. But eventually we split all these like values from our flattened table into different tokens. And these tokens really depend on the task. So some people or most people tokenize on cell level, for example. So each cell in a table becomes a token, and then we map that to a token ID in order to backtrack from the embeddings that we learn back to the tokens that were our inputs. And then we train actually this model to create meaningful embeddings. So then on to this model part, right? What is actually happening? Well, I'm assuming here a little bit of knowledge of the transformer architecture. I would definitely recommend reading that paper if you don't have it. But I think what I want to really focus on here is the difference between text and tabular inputs, where text is just like, you just have a string of text and you want to infer the meaning of a given token or word from the full context around that word. For tables, however, that doesn't really make sense. So you might need to restrict the attention. Sorry, I forgot that we're focused here on the attention mechanism. So in order to make this model attend to particular context, we restrict it in order to reflect or adhere to this 2D structure of tabular data, meaning that it doesn't make sense, for example, in this table here, which is a bit deconstructed, it doesn't make sense to just randomly attend to all cells in a table. Instead, you want to constrain these attention mechanisms to row-wise and column-wise attention. So for example, this cell Goopy in this film column on row 2, for example, doesn't really have anything to do with another cell in another column on the 3rd row. So by doing this, we properly try to reflect the 2D structure. Moreover, then you have, of course, different tasks. So we've been discussing now question answering over tables, but there's also a huge body of work on tabular foundation models where the goal is instead making predictions. So this is typically the machine learning or predictive machine learning side. And here, instead of, and this was from an older model, but instead of these token level or these cell level tokens, they instead went with tokens on row level to indicate the instances to learn from, basically these feature vectors. And here they restrict the attention mechanism. And this is, I should say, in an older version of TabPFN. I recently learned that they have, in a new version, actually cell level tokenization. But the attention mechanism here is restricting towards attention towards train versus test values in the context. So I think these are interesting ways and very helpful ways to adjust the transformer architecture for tabular data. Now, if we then fast forward to the output space, I already mentioned that you could extract embeddings from some of these models for particular tasks. So I think in the applications, we will see how, for example, table embeddings on both column level or table level are very helpful for example, inferring column semantics or retrieval. But you can also fine-tune these models on top of these embeddings, of course, to actually yield certain helpful outputs immediately. So for example, for table interpretation, particular column types, or you might want to do some imputation for table augmentation. So you might want to predict missing values. So this kind of brings us from input through a transformer model to the output. And one thing that we looked into is how well now this relational structure that we expressed as a challenge, how well these properties are captured in these models. And here we really started off with Codd's relational model, and we looked into the principles of relational data. And one thing that is inherent to relational data is that, as I already said, that this data is typically row order and column order insignificant. So basically, the order of these rows and columns isn't relevant to capture. So one thing that we wanted to understand at some point is whether indeed these properties of the data are preserved. And we looked here into, we measured the distortion of the column bendings across different row permutations. So basically we had a table, we shuffled the rows and then compared the embeddings to understand, okay, how much were they impacted by that? We did that by basically comparing the cosine similarity there. So here you can see that for some models like Turl and DoDuo, they are actually not robust to different row and column orders. And this actually is important because if our column embeddings change, if our row order is different, we see that downstream, we measured this by comparing the stability of the semantic types that were predicted. So basically the types of these columns. And we observed that in 34% of the predictions, the predicted type actually changed just by swapping the rows. But again, swapping rows should not matter as much because the type of the column doesn't change, right? So these are very interesting and relevant robustness checks that need to be happening. But of course, there have been quite some advancements to this, and there are remedies to it. But it's very good, I think, to be aware of these intrinsic properties of tabular data. So from that part, having laid the foundation of table representation learning, I want to move towards some very interesting applications that help us extract insights from tabular data. So basically, how can machine learning now help us with retrieval, semantics, and reasoning over tables? And while there is quite some work on the insight parts, so for example, asking questions over tabular data and making predictions, I realized that, from my industry perspective, it actually really all starts with having the right tables, and we should not just skip all over that. Because I observed that there is this huge knowledge gap between, understanding your task, so what you want to do, and understanding and like have full familiarity with the data that your organization, for example, has. So typically people, or like data scientists and data analysts, they know what they want to do, but they don't know which data they need for it. To illustrate this, you might have seen some data interfaces, let's say. So here you see a snapshot from Databricks from their website, where the search query is food inspections. So this assumes that someone is familiar with the underlying data that they might need for a task, and that they need somehow this table called food inspections. But I can tell you that very often the users of these systems, they don't really know what data they need. So they also don't have the right keywords, for example, to express. And we examined this hypothesis by surveying roughly 100 data scientists and analysts. And we indeed found that one of the most common methods currently for finding the right data set is still by asking colleagues what data they would need for a particular task. And also based on my own experience in industry, this took a long time to identify the relevant and appropriate data set for a given task. But this should be really not surprising perhaps for people in industry, but I think this should trigger a lot of work to improve this problem. Because how we actually want to search is, instead of on keywords or table titles, which I don't know, right, as a user of these search interfaces to data. Instead, I want to search with the problem that I have, and that the system retrieves for me the relevant data set for that problem. So how we actually want to search, and this was one of the survey respondents, you want to express, okay, I need a data set to solve a particular issue with these columns on a granularity desired. And maybe you have even more kind of requirements for the data, but that is what you want to express. So what we did recently is building this proactive dataset search engine, which actually starts with a task-driven query. So you really start off with the problem you have and the task that you want to perform. Under the hood, there are table embeddings. I won't get into much detail, but there will soon be some work out on this as well. But by bridging this gap from task to the actually semantics of the data automatically, we can really greatly improve our dataset search systems. But besides this task-driven query, we find that we really can use AI actually to give suggestions, for example, from relevant columns for a particular task. We might get input on how relevant a certain data set is for the particular task, etc. So I think these AI-powered tools, let's say, are very helpful for servicing the relevant data, because in the end, that's where everything starts. But we're also working, and I think this is also a very important direction to explore further, is to straight go for the insight. So instead of expressing a task, for example, you want to train a particular machine learning model to serve a certain problem, you might just have an insight. So just a question that that you have for data, and then you want to have this end-to-end system that gets the right data, executes a certain set of transformations, and then gets you the insight that you're looking for. So if you then would have this particular question, like what is the highest eligible free rate for K-12 students in the schools in Alameda County, what you want this system to do is to interpret and contextualize this query, then retrieve the relevant tables. Again, this is typically empowered by table embeddings, and then do some reasoning or query execution or making predictions on this data to get to the answer. But this is, of course, not very easy. First, you would need, of course, these table embeddings, but you really need to address the complexity of the tabular insights and the analytical insights that we're typically looking for. So if we're moving towards these natural language interfaces for tabular data, we very quickly realize that the kind of questions and insights that people are looking for are very compound. So it's very compositional, meaning that there are, in this query, for example, what is the highest eligible free rate, blah, blah, blah. There are different components that each have a different kind of implication. So some of this might actually indicate the relevant analytical task or filter to include in a SQL query, while other components express the data that is needed. But besides query complexity and its compositional nature of it, we are also facing, of course, inherently complex organized databases. So you can imagine that you have very large databases with many schemas, each schema with many tables, each table with many columns, etc. And you need to figure out how to then, retrieve the relevant data to these queries on the fly, let's say. So what we find is that it really requires careful query decomposition and alignment with the particular components that are in this end-to-end system. But we also need to make the retriever here, the retriever that actually gets the data, aware of all these connections between data sets. And then, so this connectivity aware retrieval, I think, is very important as well. All right, so if we have the data, where everything starts, the next question, and here I assume that you're just looking for a data set for a particular task, you might wonder, like, what is this data about? And that's another important task for many different applications in downstream applications. So for example, in data cleaning, but also data integration, predictive machine learning, and other downstream tasks, the semantics of the data is super important. Because if you look at this table, for example, here on the screen, you see some headers that resonate, some column names that resonate, but then you have pre-crop, pre-pre-crop, pre-pre-pre, probably crop. And you want to really automatically understand or categorize these columns. And this is actually a quite descriptive table. So descriptive column names, but very often you see weird abbreviations or codes as column names that no one can make sense of. And that is the goal of semantic type detection that I earlier referred to as well. And we've been looking into using column embeddings to actually then use these column embeddings to inform column types from. So back in 2019, we introduced this relatively small model actually. So just like thousands of parameters instead of the billions, or where are we at currently, number of parameters. And we just trained that model on top of these column embeddings, so vector-wise representations of columns, to predict 78 semantic types. So you can think of names, addresses, like just common semantics. And this worked actually very well. So compared to human consensus, where we asked people, like actual humans, to classify different columns in tables with these 78 types, we found a performance of 32%, like an accuracy of 32%. But with this model, we had an accuracy of 89%. And that's a very stark difference, I think. And that also makes sense, right? If you consider having to choose from a very long list of semantic types for a set of tables, well, that might get very daunting to do, but also difficult because some semantic types might actually be closely related. And that is also one of the key errors that we noticed in this type of model. Another shortcoming, of course, is that it couldn't really work with numeric data. So numeric columns, mainly because we were using representations that were coming from like the NLP area. So they had like trouble distinguishing numeric data from each other. There, of course, more context would help as well. But you might think, okay, you have this neural network trained on column embeddings. Why bother now that we have LLMs as well? Can't LLM just do this for us now? And this has been studied by Mo Kayali, actually, where they use ChatGPT, I think, or GPT 3.5, sorry, to do this annotation. They found that they call this model Chorus. They found an accuracy of 87%. But then they found for Sherlock, this tiny model that I just briefly explained, they found a performance of 93%. So that is an interesting gap. It comes very close, but it's a very interesting gap to see this huge model that can do everything versus this tiny model that's quite task specific. And I think for many of the tabular tasks, actually task specific smaller models are really great. So I see there's a lot of value in this. Also from the resource efficiency side. But it's really like a trade-off to make between computational efficiency, accuracy, but also privacy, of course. And on that notion of privacy, why would we, another interesting use case of semantic types is actually to assess sensitivity. So we have this Sherlock model, and that can also, of course, classify PII types. So for example, name and phone with actually high confidence, as we just saw. But the question that we asked, and this was also done in collaboration with the UN Humanitarian Data Center last year, is whether all PII typed values, so are all phone numbers sensitive? And are only those PII types actually sensitive, or is there, more sensitive data out there? So I think these are very interesting questions. So one concept that we introduced here is the concept of type contextualization. So imagine that you have this table with names and addresses, but you have these two tables, one with names and addresses of humanitarian workers in conflict zones. Of course, this is, if this would be public, this would have a very high risk. versus names and addresses of professors, their office addresses. This is typically public information, so that has lower risk if this would be published. So this is like, you need to really consider the whole context of the data set in order to understand whether the types, the detected PII, potentially PII types, are actually sensitive or not. Why that's important is because otherwise you were flagging all phone numbers, but you would then end up with many false positives because it's not actually sensitive. So if you're like having a manual checking afterwards, you really want to reduce the number of false positives there. But then on this question of like, are only PII typed values, like personal identifiable information, are only those PII type values sensitive? And there, from this collaboration with UN, I really realized that that's not the case. So for example, we had a like running example or hypothetical example where geocoordinates from attacked hospitals in Gaza has, of course, a very high risk if it would be published, versus geocoordinates from hospitals in Germany, which has a much lower risk. So this really reflects the concept of domain contextualization. So it really depends on the domain, but also other contextual factors. So for example, the region of this data set, where it is coming from, whether this data should be considered sensitive or not. So yeah, what we did here is we developed this type detection system that not only detects the type, but then uses an LLM actually to reflect on its sensitivity. And we found great performance improvement actually by adding this reflection step, just to understand if it's truly sensitive or not. I will speed up a little bit more in the interest of time. But for domain contextualization, what we did there is we first retrieved relevant rules from documents from the UN that specified which data should be considered sensitive. And then we provided this to an LLM along with the table in order to have it reflect on its sensitivity using those domain-specific rules. And we found that, this was a really effective mechanism actually. And the precision can be a bit better, but at least the coverage is 100%. Also because LLMs are typically quite cautious when it comes to potentially sensitive data, which I think is a good thing actually. So here is an example. So here you have this table with a column that doesn't really resonate with me per se, but by providing these rules documented by the UN, along with this table, this LLM could actually very well reason over its sensitivity of the data. So then, we've now seen retrieval, how we can surface semantics using these table embeddings, as well as how we can use these semantics to inform sensitivity assessments, which are more like data management oriented tasks. But of course, in this democratization of insights, we need to really also perform and include, of course, tabular reasoning. And here I want to elaborate a little bit on what LLMs can and cannot do. So one study that we did is asking this question, whether LLMs can answer these analytical questions over multiple tabular inputs. So we had two different tables and a question. So for example, what is the average budget of drama movies with a greater or equal to 8 rating? You might think that given the table, this would be actually quite easy to solve. But of course, this is not really the case for LLMs. And there are, of course, better tools to actually do that. But we also empirically assess that. And we see that the performance really degrades when the context, hence the tables, get larger. And this is another important property of tables, actually, we're not dealing with Wikipedia-style smaller tables. We typically deal with much larger tables. And as soon as these tables increase, we here empirically observe that the performance or the accuracy of this question answering task really degrades. And it's always interesting to look into the reasoning traces of these language models, where you can see that they are going back between different values in these cells to make sense of it. And then you see it's like, okay, I'm getting confused. It actually admits that. Other people have also studied whether LLMs can actually causally reason over tabular data as well. For example, what is the average causal effect from T to Y? And here, I want to just highlight an observation they made. So here you can see that in the table, that LLMs are actually more accurate, and particularly the larger LLMs are more accurate without the data than with the data. So apparently they are just guessing, right? They are completely ignoring the data. This was assessed using multiple choice, which I think is not a very reliable metric, but it's very interesting to see that they actually ignore this data entirely in their reasoning, which I think is a great risk. So from these observations, what I think is the better ways to use LLMs is, as I said, generate code for tool usage. So we've been working on this text-to-SQL data set, and we observed this super long question that might not be as realistic, but given this analytical question, what you then do is you provide this to an LLM, and the LLM, instead of providing the answer given the data, it just provides you the SQL code. And I think that's a very useful mechanism and much better instead. Of course, that is also not very easy, right? So there are many challenges in that, but I think that's a worthwhile approach. And of course, you can use LLMs for data enrichment and other things, as we have just seen also on this sensitivity assessment, for example. But I think for analytical reasoning and like statistical reasoning, I think it's much better to use different tools than LLMs. And of course, there are many task-specific models as well, as I said already, for predictive machine learning, for example. I think that's really cool as well. And I think this transformer architecture can be really utilized to its full power. And then with some of the remaining time, I wanted to take you through a brief future perspective, which is more focused on putting everything together. And I think this can be a promising future for data science as well. And as we see also in demos from companies, is that you now have this LLM, and as I said, it can reasonably generate code. And then for data science, you see that they can execute or like generate code for many different steps in one go, and it all looks as if it's a super successful exercise. So you would think, okay, with LLMs, we have solved the problem of data science. Benchmarks have shown that this is not the case. So here you see a benchmark for data science tasks, and the success rate is 0, mainly, except for Claude. And I think this really illustrates that it's very complex, these kind of tasks. As I said, right, these are multifaceted pipelines that each have very different requirements. So you cannot just throw a single, only generate code, for example. So much needs to happen here. So yeah, the success rate of 0 should indicate that this problem is long not solved. And if you then ask, like, okay, yeah, what can possibly go wrong? Imagine that you have this this task of analyzing the proportion of adult and juvenile animals in the census data. Are there any spatial patterns in age distribution? Okay, regardless of this task, it's, you can imagine that there are many steps involved. But okay, we first want, if we assume that the data is given, we first want to validate the data. So we generate a plan for data validation. We then execute that plan, we check it, the result, we might fix it and go back to maybe correct some of the steps that we've taken to data validation. Sure, but then you have all these other tasks, and imagine that you now put everything in one sequence, one pipeline, abstracted away from a human. This will always lead to failure. And I think this is just good to realize. And of course, there are different mechanisms that have been introduced and more like iterative, more human in the loop kind of systems as well. But I think there is so much kind of steps and involved in these processes that it's a bit naive to rely on a single LLM to do it everything. But it's getting much, much better, particularly for SQL-enabled questions, so more data analysis questions. We see that a heavily engineered system can bring the success rate from 14% to 86%. So people have been making like huge strides already, and there's a lot going on in these diagrams. So the next question is, of course, okay, it's great to see these numbers in these benchmarks go up, but how robust is this then? I think what is good to see is that there is always human involvement in these pipelines as well, in reality, eventually. So, that's more on the data analysis side, so more like SQL, etc. But we could, of course, ask like, are agents, are LLMs, and machine learning in general, representation learning, is that a threat or an opportunity? And I think one threat is that, I see threat is met with a T, but okay. What could be dangerous is if we become overly reliant on agents to do everything for us. We get very lazy, right? And we are losing control very easily. It's very hard to debug these systems and really understand what's going on if you haven't been there, leading this execution. So I think instead of, going for a human in the loop kind of framework, we should really move towards the human in the lead kind of framework. But I see a great, great opportunity. Circling back to one of my motivations is that we now can finally automate those 80% of mundane data preparation tasks. But I see a great, great role for us as humans, of course, because we have really good data science and domain context and expertise. So I think it's a great opportunity to really put everything together, and then we can make finally like data science also successful and and responsible in deployment as well. So more on the robustness side, because deploying these artifacts, these models, for example, downstream, there's a lot that actually can go wrong. And I think for us, it's very good that we now free up way more time for actual rigorous checking of these models, for biases, etc., etc. So wrapping up with the key takeaways, I see great potential for tabular native neural models for automating mundane data preparation tasks, also for making predictions, for analytical queries, perhaps more through code. But I see also great value in smaller models for very specific tasks, as we see that that's typically outperforming on accuracy. For LLMs, I see great value in enriching and interpreting data, for example, for assessing sensitivity and based on particular domain context, but also for generating code, for example, for SQL. We should not use LLMs for analytical and statistical reasoning. I hope I made that clear. And I see for the future that much is more like going into this end-to-end, albeit human navigated data analysis and data science systems. And I see a great critical role for us there as well. So here I would like to end. Also listing here all the core project leads of the work that I've addressed during this talk, as well as where the funding is coming from, of course, and the collaboration partners for this. Thanks.
Thank you very much. It was really interesting and thought-provoking, I would say. We already have some questions, so in the sake of time, I will go forward. The first one is from Erin Stein, and she's asking, where does incorporating metadata into the process take place? How do we ensure the person posing the question understands the caveats and biases reflected in the answer, so we don't train people to take responses at face value?
Yeah, so this is really a great question, actually, that we're currently looking into. I haven't seen very dedicated work on this yet, but I think so one, we need to understand when questions are answerable by the data. So if we have actual complete like data coverage, let's say, to actually provide an answer to this data. Because one risk of these models is that they typically just really try to get an answer. So we need to really assess whether the answer is truly supported by the right data. And then regarding the biases, so that's another problem that we're thinking about, how we can correct for that, or at least inform the end user, the interpreter of the insights, whether certain biases might, or like whether, this can also come from how the question was formulated, for example. There is someone here also looking into this. And this is really still an open question at the moment. I think giving transparency in what data is actually used to come to an answer is very important, so that at least, and maybe this should actually be more on a, providing or servicing or extracting certain statistics of the data. For example, how many samples there were per group to come to an answer. These kind of statistics are relevant to include.
Thanks. We have another question from Seth Caldwell about the popularity of AI-driven coding you were also talking about. So given this popularity and making data analysis and also full end-to-end digital product development available to non-technical experts, what do you think about the performance metrics? Will there be a shift so the data science tasks are now could be solvable with, for example, is citing Opus 4.6?
Yeah, so I really don't think that's the case. Well, I think we should just take the benefit of having good models and tools available, right? But we should uplift ourselves. So I think it is great that more data is used, because actually I think we're currently using 1% of all data that we're gathering worldwide. So if we can surface more insights from that data more easily, but in a robust manner, I think that is really excellent. But there are many critical tasks that these models and tools cannot do for us. And I think those tasks like this, we have problem and domain context, right? We have heavy data science expertise so that we can really oversee all risks and potential edge cases that we want to cover. So I think here we can really add a lot of value. And I think that should be a great focus point also in education, for example, for the next generation of data scientists. But we should, in terms of metrics, one, I think it's very hard to have these benchmarks reflect all domains that we might encounter, and also all kind of complexity, right? So I think this is always a limited view on the performance of these systems.
Thank you. We have one last question from Zenka Yang. Is asking, compared to a specific fine-tuned LLM in certain domains, do you think using prompt engineering-based LLM agent can achieve equivalent performance? For example, equip the agent with tools, domain knowledge base, etc. Since many commercial LLMs are developing very fast, I'm curious about the gain of LLM fine-tuning.
So I think here it's also about computational efficiency. So besides performance, right, we already noticed that for certain tasks, LLMs aren't good at everything. And you can of course provide a particular model as an input to an agentic pipeline that uses LLMs, for example. So a specific fine-tuned model might be part of that toolbox. But other than that, I think maybe for particular tasks, you want to use an LLM that is equipped with all tools and whatnot. But if you're, thinking about semantic type detection, for example, for a particular downstream task, maybe then a small specific model is all you need. And similarly, we're working on, for example, smaller text-to-SQL models, where using these huge models just doesn't. Why would you use that? It's also very costly, right? To do this. So I do see benefit in fine-tuning specific smaller models.
Thank you. And Patricia Del Boca is asking if there are benchmarks of the text to SQL tools, and how accurate and trustworthy are they, or can they be?
Yeah, that's a good question. So I think there are now more and more realistic benchmarks. So you have BIRD, BIRD, and Spider 2.0, which are text-to-SQL benchmarks that try to reflect really the complexity of real-world data contexts and databases. But of course, there are still limitations. So we're also working on this new data set that has even more realistic properties and coverage of data. So it's very hard to cover everything, but these are the main benchmarks that are currently state of the art, let's say, in terms of representation of industry level tasks.
Thank you very much. In the sake of time, if this is okay with you, I would like to conclude the session. And before concluding, I would like to thank you very much. It was really interesting, as I said before, and insightful. And today's discussion has highlighted both the progress and especially the open challenges in Tabular AI. And from my point of view, it has given me much to reflect on, not only in terms of technology, but also in terms of the evolving role of the data scientist. Thank you very much, and thank you also for the active participation online. We look forward to probably continuing this conversation in future sessions.
Thank you so much. Thanks, everyone.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.